Yeah, so we're just doing Ansys demonstrations today, and so if you want to follow along, you can follow along. But if not, just just you can just chill and watch.
Hey, Professor,
Hey, how's it going?
I've got a question.
Sure. What's up?
So what happened to the free version of Ansys that we could download? It seems to have disappeared.
It disappeared? Like it's not on
Yeah.
your computer anymore?
No. You know the school website where we can download free software?
Oh, I see. Oh, it was on there before.
Yeah, if it's there, I'm not noticing it.
Okay. I usually I download it just straight from the Ansys website, and so usually
Oh,
I just
okay. Never mind.
Google it. So download Ansys student. Yeah. So because Ansys provides a free version, and so we just use that one.
Okay.
Yeah. So we do Ansys student, and then yeah, this one right here, Ansys student 2021. Mm-hmm.
So I think I got hammered on the exam.
Mm-hmm.
Are we going to go over it today?
I haven't looked at them yet, and actually, I think one more person needs to make up the exam still, and so I wasn't planning on grading them probably until probably later this week.
Okay.
And so probably maybe beginning of next week, if if there's if there's enough demand, then I'll go over it then.
Okay. Thank you.
Mm-hmm. Dogecoin till Saturday. One of my friends just cashed out Dogecoin. Actually, she made a decent chunk of money. All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Second to last week of class. It's almost summer break. It's so close that you can feel it. You can literally feel the temperature. It's getting hotter. Okay. All right, so last class we had our midterm, and so judging from a lot of the reactions that I've seen, it seemed to be a pretty tough one. Right. So I haven't started grading it yet, and so I'm a little bit slammed this week in terms of other stuff, but I'm hoping to get it graded by the end of this week, and so I'm hoping by Thursday class, and then, but if not, definitely by Friday, I'll have that stuff graded. Okay. All right, and then after I grade it, probably by next Tuesday, we can talk about the exam, and then any adjustments. I depending on what the scores are, I'll have to see. I'm thinking about curving it or adjusting the grades, either one way or the other, but we'll see. So I need to grade it first, and then we'll go from there. Okay. All right. And so the plan for this week is, we're just going to be doing all Ansys stuff this week. And so today we're going to be doing more Ansys demonstrations. Okay. And so I have at least two for you guys planned today. And so it's going to be how to create surfaces for force application in Ansys, and also heat transfer simulations in Ansys. Okay. And so we're definitely gonna get to those two. And then Thursday this week, we're going to do another Ansys activity. And so that's the final one. And so the activity Thursday is going to be on topology optimization. Okay. And I just realized something that I included an extra assignment this semester compared to what I promised you on the syllabus. So I think on the syllabus, I promised 8 homework assignments, and then the Ansys activity this Thursday will be the 9th, if you count kind of the 3 written homeworks that we've done. And so I'm going to make the Ansys activity this Thursday optional. And so if you do it and you turn it in, I'll give you just a little bit extra credit, not that much, but it's not going to be required. And so I think I'll probably give you maybe like 20 points extra credit on your on the homework grade. Okay. But since in the syllabus I promised 8 homework assignments, and so the 8th one would be Ansys activity 5. And so I'm not going to make you guys do an extra one, especially since I know a lot of you guys are starting to focus a lot more on your projects. Yeah, the lowest homework is still dropped, and so that should automatically be done by Canvas. And so Canvas should already see what your lowest homework score is, and it's going to drop it. Yeah. And so the fact that Ansys activity 6 is going to be optional has no bearing on that. And so your lowest homework out of our 3 written homeworks and our 5 Ansys activities so far, the lowest one of that one will be dropped. Yep. And then Ansys activity 6 will be optional, and so you can turn it in for just a little bit extra credit, but if not, it's not going to have a negative impact on your grade. Okay. Progress reports are due this Friday, and so remember the progress reports. They're just it's just a check-in, And so, just let me know how you're doing on your final project, and any feedback that I can give you, any help, I'll be sure to do that. And so I'll be I'll be giving you feedback on your progress reports probably at the beginning of next week, just because this weekend I'm a little bit busy. Yeah. All right. So you can skip Ansys activity 5. So if you've gotten 100% on all the other assignments, then yeah, you can skip Ansys activity 5 and it'll be dropped from your grade. Yeah. You're gonna need that in right. Okay, I'll send an announcement out to say that Ansys activity 6 is optional. Yeah. Yeah. So I'll send an announcement just so everyone is on board, just because oh, actually we have 30 people, and so I know it's late in the semester, it's all virtual, and I know people have projects and stuff to work on. So yeah, I'll send in emails just to confirm that and to let everyone know. All right, and so are there any questions I can answer before we get started for today? Okay. All right, and so let's go ahead and continue where we left off last Tuesday. So last Tuesday, actually, there was a little bit more that I wanted to show you, because the last thing that we were doing was learning how to do fatigue analysis in Ansys. Okay, and so to set up the fatigue analysis, we basically set up kind of the same thing as a typical static structural analysis. The only thing that we add to this is this fatigue tool. Okay, and so just to remind you, the way that we got this fatigue tool is we right-click on solution, A6. Okay, so this is typically where we would insert things like the total deformation, the equivalent stress, things like that. Okay, but another thing that you can insert here is this fatigue tool, and so that'll give you information of how many loading cycles that your part can withstand before it dies to fatigue. Okay. All right, and so I think last time we were looking at this screen right here, and so if you left-click fatigue tool, then you will be able to have some control over how the loading goes and what kind of mean stress correction theory that you can apply. Okay. All right, and so the loading, remember, you can either switch it, and so the two main ones that you can do are either fully reversed. Okay. And so what this will do is that it'll apply your loads completely forward in one direction, and then it'll reverse it and then apply the load in the other direction. Okay. And it'll cycle through this, yep, over and over and over again. And then another way that you can apply this is zero-based, okay, where in this loading condition, your load will go from full blast down to zero, to full blast down to zero, and then oscillate up and down like that. Okay, and so depending on the loading situation for your part, you can choose either one of these, whichever one makes the most sense to you. Okay. And then the other thing you have to select here is a mean stress theory. Okay. And so these, usually I think you would want to have a mean stress theory that kind of slopes downward like this, okay? And so this one is the Solderberg theory, right? And so this will tell you that the basically the yield of this material will kind of decrease. The yield strength will decrease over time, okay? But again, this is not something that I'm particularly familiar with, and so I'm not going to pretend that I know what these different models are. And so, if it's, if you have a mean stress theory that you've learned in another class, like strength of materials, then definitely apply that here. But it's been a long time since I've taken that, and so, I'm just choosing the one that's been recommended to me, by just reading some stuff online and reading the documentation. But probably you guys are a lot more knowledgeable than me on this stuff. Okay. All right, and so after you pick the loading style and also the mean stress theory, then you can go ahead and run the results, and then you can get the these two main results here. Okay, let me go ahead and solve this one more time. Okay. All right, and so the first result that we can look at here is called life, right? And so life here will tell you how many loading cycles that your part can withstand before it starts to become in danger of fatigue failure. Okay. And so what you would like to see is you would like to see that most of your part should be a blue color here, okay? And so blue is typically a good color to see in Ansys, because blue tells you that it's either low stress or it can take a lot of punishment, okay? And so you can see for the majority of this part right here, we have the maximum allowable loading cycles, which is 100,000, okay? And we're limited to 100,000 in this case because that's the maximum of the SN curve that we saw last time, okay? And so I think this material is structural steel. And so for structural steel, I think we only have data for up to 100,000 loading cycles. And so that's the maximum there, okay? And so this is not saying that the part will fail after 100,000 cycles, but it should last at least 100,000 cycles, okay? And if you want to see how many more cycles it can withstand, you would need to input more data into the material properties in the way that we showed last time, okay? But let's look at the other end of the spectrum here. And so the other end of the spectrum we have in red, and you can see here, the red here is about 56,000, okay? And so 56,504, okay? And you can see that those are occurring at these kind of apexes here on the hole, okay? And so what this tells you is that, you know, after you reach about 56,000 cycles, then these parts of your model will be in danger of fatigue failure, okay? And so you repeat this and you repeat this loading, you know, forward and back, 56,000 times. Then where your part is going to fail first is over here, okay? Which is highlighted in red and yellow and green stuff, right? And so this makes sense because if you look at kind of the equivalent stress field, you know, this is where the stresses tend to concentrate in your model, right? And so it makes sense that the areas where the stresses, the mechanical stresses concentrate, those are going to be the areas where it's going to fail first due to fatigue, okay? All right. And so another thing that you can find here is the safety factor, okay? And so the safety factor is a measure of you know, how well this part will hold up, okay? As a function of time, right? And you can see here the minimum here is 0. And so what that tells you is that Ansys thinks that, you know, the safety factor for these areas here, which are in red, are really low because they're gonna fatigue and break, you know, at a very relatively fast time compared to the other parts, okay? And even though the other parts of the plate didn't fail, at least not in the life calculation, what you can see here is, you know, Ansys is giving you some other areas which you know, you should maybe be concerned about, you know, in case for future fatigue failure, okay? And so you can see here that, you know, the maximum safety factor here is blue. And so in these areas that are blue, those areas are good. But in the areas that are orange or green or red, you know, those are some relatively dangerous areas where, you know, you might want to think about redesigning in order to make that stronger, okay? All right. And so this was an overview of the fatigue life tools within Ansys. And so remember, you know, these are only an approximation. And so it's not like Ansys is actually simulating 100,000 cycles of the loading. And so it's using, you know, it's using finite elements as well as, you know, some theory about fatigue in order to produce these approximations. But in real life, you know, your results may be a little bit different than this, okay? And so don't treat this fatigue tool as something like gospel, and don't say that, you know, I know for sure that this part is going to last for exactly 56,504 cycles before it breaks, okay? And so it's more of a, think of this tool as more as kind of like a guideline to help you say, you know, okay, I can see that this area of my model here this area is more vulnerable than the other ones. And so let me try to beef up this design here to make it a little bit better, okay? And so, you know, for these ones, because it's such an approximation, I would take these as kind of just kind of a guideline to help you kind of design your part a bit better, but nothing, you know, nothing too truthful. I mean, not truthful, but nothing too exact. There's nothing super exact about this. Okay. Okay. So any questions on this fatigue tool before we move on? Okay. All right, so let me go ahead and close this, and then we're going to move on to the next Ansys demonstration. Okay. No, don't want to save. Okay. And so the next Ansys demonstration is for how do you actually create different surfaces in your model for force application. Okay. And so let me show you a figure here just to kind of show you what I mean by that. Okay. Okay. And so here's and so this is a handout that's been posted onto Canvas, and so this is available for you guys to look at. Okay, but what I mean by this example is, you know, we want to create situations that look like this. Okay, because normally, you know, if you have kind of a cylindrical part like this, and you try to select the surface of that part, you're going to select the entire exterior surface of the cylinder. Okay, you know, which is fine for a lot of cases, but you know, there might be some instances where you only want to apply boundary condition on just a small area of this of whatever part that you have. Okay, And so I chose a cylinder here because this is kind of the most common place where you would want to use this. Is because if you have some kind of rounded geometry, you know, and you want to apply a boundary condition on just a small part of that geometry, you know, right now you're not able to do that within Ansys because it's because if you try to select the surface, it would select the whole thing. Okay. And so one example that uses this is, let's say that you have some kind of wheeled object, right? I know several of you are doing like skateboards or longboards, or some of you are doing cars or trucks or things like that. Okay. And if you wanted to apply a boundary condition on the bottom of the wheel, right now you're not able to do it because you try to select the wheel, the cylindrical wheel, and you just select the whole thing. Okay. But what would be more realistic would be is if you could only select just a small portion of it, so that you can say that, you know, this is the area where my object is be resting on the ground, and so that's where I want to apply my boundary condition. Okay. And so the purpose of this demonstration here is to show you how to create these kind of extra surfaces for the express purpose of boundary condition specification. Okay. All right. And so let me go ahead and create the geometry for this. Okay. And so the tool that we're going to use for this is Design Modeler, which is the first CAD software that we learned in Ansys. So let me go ahead and boot this up. Okay. And the tool that we're going to use inside Design Modeler for this is called Projection. Okay. All right. So the first thing we're going to do is let's go ahead and create our initial geometry. And so I'm just going to create just a simple cylinder here. Okay. So let me go ahead and draw a circle here. Let me go ahead and dimension this guy. Okay. And remember, you know, I'm going to go a little bit fast for these demonstrations because remember they're just demonstrations, and so you know, you're not turning anything in for these guys, and so you know I'm going to go a little bit fast. But if you ever have any questions about or you want to see me click something again, just go ahead and shout it out. Okay. All right. And so we have our circle. Let's go ahead and extrude it. Okay. I'm going to go ahead and extrude it 20 centimeters in this direction. So I'm going to hit generate, and here is our barrel or wheel or whatever cylindrical object that you want. Okay. All right. And so, you know, if we want to apply a boundary condition on just a small part of this wheel, you can see here that I try to select a surface, and the only surfaces that I can select here are either the top cap, the bottom cap, or the entire lateral round surface. Okay. And so we don't want that. And so we, you know, let's say that we only want to apply boundary condition on just a small portion of this cylinder, you know, kind of like what we have right here, which is this patch that I have. Okay. And so what we need to do is we need to project another sketch onto the cylinder in order to create this extra surface. Okay. All right. And so we're going to use several different new tools here in Design Modeler. Okay. And so the first of which is we need to create a new sketching plane. Because right now, the only sketching planes that are available to us are the three Cartesian planes. And so we have the XY plane, the YZ plane, and the ZX plane. Okay. And so I want to create a plane that's going to be offset from this. And so we're going to bring basically the plane off to the side here. Okay. All right. And so to create that, let me go ahead and come up here and go to Create. Okay. And then from this create tool, you can do a lot of CAD, CAD specific software stuff. But in this particular case, we're going to click on New Plane. Okay. And you can see here that we've created this new plane called Plane 4. And then we're going to modify this. Okay. All right. And so the first thing we're going to select here is we're going to select the base plane. Okay. And so the base plane is basically going to be the plane that it's going to be parallel to. And so in this case, we have two options. We can either pick the XZ plane, okay, and you can see the XZ plane is kind of in plane with the side of the cylinder, or the other option here is the YZ plane. And so the YZ plane is just this one right here. Okay. And so because we have a cylindrical object, we can choose either one of those, and they'll both work. Okay. The only one that we can't choose is the XY plane. Okay, because the XY plane, that looks, if we're looking down the XY plane, that's going to be the ends of the cylinder. Okay, and so we want a plane that's going to be on the side so that we can project a surface onto the side of that cylinder. Okay. All right, and so for this example, let me pick the YZ plane. Okay, and so to select a base plane, you can click on base plane here, click on another plane here from the tree outline, and then go ahead and hit apply. Okay. Right. And then from here, we want to do an offset, okay? And for the offset here, you have to be a little bit careful because we want to offset this plane, in this direction, right? Because our plane right now is currently in the YZ plane, okay? And we want to bring that plane basically out of the page. And so it's offset from our cylinder, okay? And so right now, if you look at kind of the coordinate axes for this particular plane, you can see that the axis here that brings it out is going to be the blue one, which is going to be the z-axis, okay? And so you have to be careful here because this z-axis is not the same as the global z-axis. And so the z-axis here is going to be the one that's local to the plane that we just created, okay? And so when you're offsetting your planes here, make sure you look at the coordinate axes for your new plane and not the global axis here. All right, and so we're going to quick transform here. And so in the transform, we're going to click on offset z, okay? And so that's going to bring the plane out in the z direction, right? And so let me offset this plane by 15, okay? Because I know the radius of the cylinder here is 12.5, okay? Because I picked a diameter of 25, right? And so picking an offset of 15 will bring this plane out from the cylinder, okay? And you can see here from the from what I have on the screen here that now this coordinate axis system is brought away from the origin and is offset out by 15 centimeters. Okay. All right. So any questions on this so far? Okay. All right. And so now that we've offset this plane, we're ready to draw a sketch in this plane, right? And so the sketch, you can almost think of it as almost like a stamp. And so this is going to be what we're going to stamp onto our surface and our stamp onto our cylinder in order to create another surface. Okay. All right. And so let's go ahead and we have the lightning bolt here. So let's go ahead and click generate. Okay. And so by clicking generate, we can see that, our plane here is activated. Okay. And so let's go ahead and create a new sketch in this plane. All right, and so in order to create a sketch in this plane, make sure you have plane 4 selected here. Okay, so that's the new plane that we just created. Let's go ahead and click sketch, okay? And let's go ahead and just make just a simple rectangle, okay? Let me center this. Oops, rectangle, okay? And let me make a rectangle that's just like this, okay? All right, let me just go ahead and dimension this rectangle here just to make it good. Okay. So the length, let's make it the same length as our cylinder. Okay. And let's have the height of this be 10 centimeters. Okay. And then let's set the distance in between these two guys to be 5, just so it's nice and center. Okay. All right. And so if I rotate here, you can see that I have this plane that's right here, or this sketch right here. Okay. And what we're going to do basically is we're going to project this sketch directly onto our cylinder here to almost act like a stamp or like a tattoo. Okay. Okay. And so next thing we have to do here is we have to freeze this sketch. Okay. And so let me go back and go to the modeling portion here. Okay. Let me highlight the sketch here. Okay. And so the next step we have to do is we have to freeze it. Okay. And so what that basically means is, we're going to be indicating to Design Modeler that we've created the sketch here, but it's actually not going to be part of our model. Okay, so we don't want to create any new volume with this. We don't want to create any new geometry because we're just using this strictly for just projection purposes. Okay, and so we need to freeze this sketch in order to do that. Okay? And so you can do this, a number of different ways. But the way that I learned to do this is to use the extrude tool. Okay. And so basically the same tool that I used earlier to produce this cylinder, but now we're going to use it to freeze this sketch. Okay. All right. And so after you click extrude, go ahead and highlight your sketch here and hit apply. Okay. And so that's going to set sketch 2 to be kind of the active, mode here for this extrusion. Okay. And then what we're going to do here is we're going to change this operation. Okay. Because normally the normal extrude operation is you add material to your geometry. Which is what we did kind of in the first step before, okay? But now what we're going to do is we're going to just freeze it, okay? And so under operation here in the details view in the bottom left, what you're going to do is you're going to change this to add frozen, okay? Right? And so by changing this to add frozen right here, then that's going to freeze the sketch and let Ansys know that we don't actually want this to be part of our geometry. We're just using it for projection purposes. Okay. All right. And so the depth here, it doesn't really matter because we're just freezing it. Okay. And so after you click add frozen, go ahead and click generate. Okay. And you should see a block that kind of appears like this. Okay. And so it looks transparent. And that's because this sketch is not part of our model. We're just using it for projection purposes. Okay. Okay. So any questions on this? Okay. All right. And so now that we've created this this frozen part of the geometry here, now let's actually go ahead and project this. Okay. And so to project, you need to go to Tools up here. Okay. And then you need to go to where is it? It's not earlier. Projection right here. Okay. And so this projection will take this sketch and project it onto our geometry. Okay. So I'm gonna go ahead and click on this projection. Okay. And you can see here that we've created a new projection object. Okay. And we need to select two different properties here for the projection. And so the first thing we need to select are the edges that we want to project. Okay. And so let me go ahead and do that first. And so I'm going to go ahead and select the four edges of this sketch right here. Okay. Using Control and click. Okay. Making sure all of them are green. Okay. And I'm going to go ahead and hit apply. Right. And so this now we have now we're indicating to Ansys that we're going to project this this sketch. Okay. And then from here we need to select a target. Okay. And so for the target is going to be the surface that we want to apply this projection on, which in this case is going to be the side of the cylinder. Okay. All right. And so we've gone ahead and selected the the side of the cylinder here for the target. Okay. And then once we're done with that, we can go ahead and hit generate. Okay. And then after we generate, it's a little bit hard to see, but you can see that our side of the cylinder here was kind of segmented into two sections. Okay. And so we have the part where we projected onto it. So this rectangle here is the projection of the sketch onto the cylinder. Okay. And then we have everything else. Okay. All right. And so now that we have this projected surface here, now we can actually use this in our simulation and apply a boundary condition onto the sky. Okay. All right. So any questions on this so far before I show you how to use this in Ansys Mechanical? Okay. All right. So let me go ahead and close this out. And let me go ahead and start launching Ansys Mechanical. And so for those of you who have final projects where you have kind of an awkward surface, or you have something that you want to apply a boundary condition on, but you don't want to select the entire surface, this is how you would do that. Okay, and so you need to load your CAD geometry into Design Modeler, create a projection, and then use that projection to apply your boundary conditions. Okay, and so I know a lot of you are doing kind of like some wheeled objects, and so that would be great to use for that. Okay. All right, and so let's see. So for right now, we have our object in here, okay? Okay. And so, let me go ahead and suppress this, okay? Because we don't want that frozen part, right? And so now all we're left with here is just this this geometry here with this projected surface. All right, so let me go ahead and mesh this, just a very basic mesh first. Okay. And then now let's apply the boundary conditions. All right, and so let me do kind of a pretty common case where let's say that this here represents the wheel of some kind of wheeled objects, maybe like a skateboard or a car or something like that. Okay, and we want to designate that the wheel is going to be resting on the ground. Okay, and so to indicate that the wheel is resting on the ground, you can apply a fixed support boundary condition on just a small portion of the wheel, just like this. Okay. All right, and so I've gone ahead and supplied a fixed support onto just the small patch that we made earlier. Okay, and then let me go ahead and apply a force, and let me just apply it on this surface right here. Okay, and so let me apply a force of let's say 5,000 newtons. Okay, and then let's look at the total deformation. oops, not directional. And so let's do deformation total. All right, so let me just go ahead and solve this just so you can kind of see, what the results look like. Okay. All right, and so now we're looking at the total deformation field of this part. Okay, and so you can see here in the small patch that we had down that we defined earlier, the deformation there is 0 because we applied a fixed support, and then the displacement everywhere else is non-zero. Okay, right. And so this is kind of a simple technique that you can use if you have kind of an awkward surface in your CAD geometry, and you want to apply a boundary condition on just a small portion of that awkward surface. Okay? And so this is useful. And so using this, you'll be able to apply your loads and constraints, much more precisely, rather than just being limited to just the surfaces that are naturally created by your CAD geometry. Okay, so any questions on this before we move on to thermal simulations in Ansys? Okay. All right. Yep, so it's 4:30, so we are right on schedule. And so let's go ahead and move on to thermal simulations in Ansys. Okay. All right. And so everything that I just showed you, all of that was listed out in this handout. And so, you can look at this handout. It has a bunch of screenshots and everything. So, you can refer to that as well. I think that's a little bit more convenient than, watching the video again. Okay, and so now let's get into thermal simulations in Ansys, right? And so this is a little bit different, okay? Because up until this point in the class, we've mostly just been focusing on structural funded elements, okay? Especially in the Ansys portion. But just like we talked about before, Ansys can do a lot more than just structural simulations, okay? And so if you look at kind of the toolbox that's available to you here in Ansys, you can see that there's a ton of different stuff that you can do, okay? Right? And so, I'm going to do my best to kind of cover as much as I can in terms of Ansys stuff, but, we're only just barely scratching the surface of what Ansys can do, okay? And so one big part that I did want to go over was how to do a thermal simulation, okay? So that you can do kind of heat transfer, either for your projects or for, anything else that you want to do. And so I know a few of you guys are doing thermal simulations for your final projects, and so hopefully this will be helpful for you guys as you formulate that. Okay. Okay. So, but before I do that, I do want to go over some quick theory, and so let me go ahead and stop sharing here. Let me go ahead and bring up my iPad. Because, in order to properly understand kind of the thermal simulations within Ansys, I think we need to review a little bit of heat transfer along the way too, okay? And so if you've taken 407 before, hopefully a lot of this is just going to be a refresher. But if you haven't taken 407 or you're taking it right now, maybe this will help you review for your final or help you teach it, okay? Okay, and so we're going to do just a very quick kind of Spark Notes, just a really quick summary of heat transfer, okay? Right. Because in order to kind of really understand all the settings and all the boundary conditions in Ansys for heat transfer, for thermal simulations, you have to understand a little bit of heat transfer, okay? All right. And so let me just start with just kind of a general statement of all of heat transfer, okay? Just to kind of build your intuition for things, okay? And so for structural simulations, we kind of have a general idea of what tends to happen in structural simulations. Because if we know that if you take an object and you apply a force to it, it's going to bend, it's going to deform, right? And so applying a load will cause an object to deform. Okay, you know, maybe you haven't thought about it like that, but you know, that kind of background intuition is kind of, you know, working with you, you know, whenever you're doing a structural simulation, in order to help you do a sanity check on the results, right? Because we talked about how important those things are. Okay? And so for heat transfer, you know, the kind of the one sentence summary that I want you to keep in your head all the time is that heat will flow from hot stuff to cold stuff. Okay? And so I joke with my 407 classes all the time that, you know, I say this on the first day of class, and I said, all right, that's heat transfer. That's it. That's all you need to understand. Because if you understand that, you know, heat goes from hot things to cold things, you know, that's you know, that's kind of the underpinning principle for all of heat transfer. Right? But you know, we know of course that, you know, in order to really understand heat transfer, you know, it's not enough just to say that heat goes from one place to another place. We have to quantify how much heat is going from one place to another place, right? And Ansys is a tool that can help you with that. Okay, but as long as you kind of understand this intuition right here, it's going to help you a lot when you're interpreting your finite element simulations. Okay, all right. And so with thermal simulations, let me go ahead and kind of draw some connections between, you know, what we understand from structural finite elements to thermal. Okay, all right. And so first, I'm going to talk about kind of the idea of constraints. Okay. All right, and so for structural FEA, right? When we talk about constraints, what we mean are boundary conditions that that specify the displacement. Okay. Okay. And so when we talk about constraints, we know to think about things like fixed constraints, right? So fixed constraints are, you know, when we say that the deformation or the displacement at a certain area is going to be 0, right? Okay. And so we talk about constraints and structural, you know, we're talking about displacements. Okay. When we talk about thermal constraints, you know, we're not really talking about displacement here. You know, what we're actually talking about are going to be temperature. And so when you say that, you know, you're applying a thermal constraint onto an object, what you're really doing is you're specifying the temperature at a certain location. Okay. And so this is kind of the same thing as applying a boundary condition on the displacements. And so, you know, we've seen this already, you know, when we went over strong form, weak forms, and finite element forms, right? So when we were applying our, you know, our essential or Dirichlet boundary conditions for heat transfer, it was always on the temperature. Okay. And so the idea, and so that idea translates to thermal, you know, by specifying the temperature. Okay. All right, so now let's talk about loads. Okay. And so for loads, okay, structural loads, you know, we're almost always talking about some kind of force or maybe some kind of pressure. Okay. Anything that has units of like newtons or newtons per meter square, pascals, things like that. Okay, because we know that these are kind of the driving forces that's going to make our parts deform. Okay, and so for thermal, kind of the idea of loads becomes a little bit expanded here. Okay, and so kind of the first thing that that you'll take. The first thing that you'll consider a load in thermal simulations is heat flow or heat flux. Okay. And so I think this is probably the direct analogy between these two. Okay. And so when you apply a heat flow or you apply a heat flux boundary condition, it's the same thing as if you're applying like force or pressure in a structural simulation. Okay. But for heat flow and heat flux, you're specifying a prescribed amount of heat that's going to cross into or out of your model at a certain location. Okay. All right. And so that's kind of the biggest connection. But in thermal simulations, we have to think of some other things as well. Okay. And that's in the form of convection and radiation. And so convection and radiation are other ways to specify, the amount of heat that crosses over a surface in a model. It's just that they're applied in different ways, okay? And so, what I'm going to do here is I'm going to go through, kind of all the essential information. I'll review what convection is, what radiation is, what heat flux is, and then we're going to do an example in Ansys of doing a thermal simulation on a fin, okay? All right, so any questions on this so far? Okay. All right. And so if you want to solve a thermal simulation, basically the equation that you're solving for is the heat equation. All right, and so the heat equation looks something like this. So we have partial t, partial squared t, partial x squared plus partial squared t, partial y squared plus partial squared t, partial z squared, okay? So this is the most general form in 3 dimensions, okay? Plus q dot, which is a thermal generation term, and f, which has all of our external loads, okay? All right, and so you don't really need to, this is kind of just for trivia in case you're wondering, what equation Ansys is solving for underneath the hood, okay? All right. And so in order to select this within Ansys, the type of analysis that you need to do is called steady state thermal. Okay. And so if you select steady state thermal from the Ansys toolbox, then that's essentially what you're going to solve. Okay. All right. And so now let's talk about the next few steps in the FEA process, which is geometry, connections, materials, and meshing. Okay. All right. And so for these parts, nothing really changes as part of your finite element process. And so you're going to follow basically the same, procedures that you've done before. And so if you have a CAD geometry, you would import that into Ansys. You would select its correct materials, you would apply its connection, and then you would do your meshing. Okay. But two things I want you to be careful of in this section here. Okay. And so first is going to be the materials. Okay. And so one thing you need to check is you need to make sure that your material, whatever you select for this one, has all the thermal properties available to it. Okay. Okay. In particular, the one that you really need to have is called the thermal conductivity. Okay. And the units for thermal conductivity are typically watts per meter degrees Celsius. Okay. And so if you're using a built-in material in Ansys, it should have this stuff. But it always pays just to kind of check just to make sure. Okay. All right. And just like Young's modulus, your thermal conductivity here can be anisotropic. But for now, I'm just going to assume that's an isotropic material. Okay. All right. And so the next thing I want to talk about is the meshing. Okay. Right. And so for the meshing, there's really not much that's different here. And so the only difference is that here you can use linear elements. Okay. Okay. And the reason for that is, linear finite elements, they don't have, or in thermal simulations, there's no risk of doing any shear locking or any stuff like that. And so linear finite elements is okay. Okay. And so that should save you actually a little bit of cost. Because then your elements are going to have less nodes, and then you can mesh it to be a little bit tighter than you've done before. Okay. But besides those two differences, nothing really changes from our usual FEA process. Okay. All right. So any questions on this? Okay. All right, and so now let's talk about boundary conditions, because this is where we're going to spend most of kind of the our time here. Okay. And so what I'm going to go over next is kind of all the main kind of thermal boundary conditions that you can apply in Ansys and what they all mean. Okay. All right, and so the first one that we're going to go over is going to be the temperature boundary condition. Okay. And so this is kind of the simplest boundary condition that you can specify, right? And it's also the if you know the temperature at a certain location in your model, this is great, because what this does is that it specifies that a surface has a fixed temperature. Okay. And so it's the same thing as like a constraint. Okay. And so you're basically forcing an entire surface to have a certain temperature. Okay. And so this is usually good. Okay. And so if you know this, then that's great. But sometimes this can be a little bit hard to do, especially for some complex geometries, right? And so the next type of boundary condition that you can apply is a heat flow or heat flux boundary condition. Okay. Right. And so this specifies the basically the amount of energy or the amount of power that's crossing over a surface in your system. Okay. And so this is nice, because a lot of times it's relatively easier to think about thermal situations in terms of energy. Okay. And so I'll give you one example of this. Okay. And so let's say that you're going to do a thermal finite element simulation of a combustion chamber. Okay. Okay. And so I'm going to draw kind of a very crude picture of one. Okay. Right. My combustion chamber is shaped like a potato for some reason. Okay. And then inside this combustion chamber, you have a controlled, combustion reaction that takes place. Okay. Okay. And so there's our combustion reaction, which looks like an explosion. Okay. Here's our combustion chamber. Okay. And then what we want to find out through FEA is we want to see, how the temperature in our conduction chamber walls, how does that how is that being affected by the combustion reaction? Okay. Okay. All right. Oh, question? Is that a Karibo? It could be. It could be an angry Karibo. Yeah. Okay. And so, let's say that you're going to go about solving a finite element analysis of this. Okay. And you want to do a finite element analysis of the combustion chamber walls. Okay. And in order to run your FEA, you have to apply boundary conditions on your chamber. Okay. And so one surface that's going to be key in your analysis is what boundary condition do you apply for this inner surface? Okay. Right. You can try to supply a temperature boundary condition, and so you can you can try to say that the temperature on this inner surface is going to be something. Okay. But that's going to be really hard because in order to really get that, you either have to have a very strong knowledge of of this combustion reaction and how hot it's going to burn and how that's going to transfer to the walls, or you have to have some kind of thermometer that's inside the combustion chamber in order to measure those things. And neither of those are very practical or particularly easy. Okay. Another way that you can approach this problem is to say that, okay, inside this combustion chamber, I have this combustion reaction going on. Okay. And based on the amount of fuel and the amount of oxygen and the amount of stuff that I'm putting in there, I know how much energy that this reaction is going to release. Okay. Right, and that's something that's relatively easier to compute than trying to figure out how hot the combustion reaction is going to be. Okay, especially because the combustion happens so quickly. It's hard to say that what the temperature is going to do. Okay, as a function of time. And in a lot of sense, that's probably what you want to be simulating for. Okay, but computing the amount of energy, that's easier to do. Okay, because a lot of times these systems are very tightly controlled in the amount of fuel and the amount of oxygen and stuff like that that's used. Okay, and so what you can do for a boundary condition is you can take that energy, okay, and then use that to apply a heat flow or heat flux boundary condition on the inside of your chamber. Okay, and so that would be a little bit of an easier and probably more accurate way to simulate this rather than trying to guess the temperature on the inside of this chamber. And so the heat flux boundary condition, I think people tend to shy away from it a little bit because it's a little bit more nebulous. But if you think about it in terms of energy and how much energy is going to be taking place here, how much energy is it going to absorb, the heat flow and heat flux boundary conditions could become a lot, they become a lot more useful. Okay. Okay. So any questions on this?
No questions here. Could I see the differential equation page again?
Oh, sure. Yep.
Thank you. Perfect.
Yep. Mm-hmm. All right, and so that's the heat flow, heat flux boundary condition. Okay, and so let me give you kind of a special case of the heat flow, heat flux. Okay, and it's so special that it actually has its own option within Ansys because it's used a lot. And that option is known as the perfectly insulated boundary condition. Okay. And so the perfectly insulated boundary condition is a special case of heat flow, heat flux, which says that for a certain surface, if it's perfectly insulated, then no heat can pass through this surface. Okay. All right, and so this would be a really useful boundary condition if you know that there are certain surfaces in your model that aren't going to conduct any heat. Okay, and so one example is, let's say that you have a certain part of your model that's surrounded by styrofoam. Okay, and so one thing that we know about styrofoam is that it's an excellent insulator, right? That's why they make coffee cups out of styrofoam. So you can pour hot coffee and your hands will not be burned, right? And so if you have your model that's surrounded by styrofoam, then you know that it's going to be act like a very good insulator. Okay, and so perfect insulation means zero heat flux, zero heat transfer. Okay, and so in reality, it's impossible to have a perfectly insulated boundary condition. Okay. Right. So I don't care how much money you paid for your hydro flask, that thing's not going to keep your water cold for all of eternity. Okay, and so all surfaces will leak heat, to some degree. And so a lot of materials and a lot of good design will limit this, strongly, but it's really impossible to have a perfectly insulated boundary condition. And so, and so for practical purposes, you don't apply a perfectly insulated boundary condition because there's going to be absolutely no heat. But it's a lot of times it's a very useful approximation and it's an approximation that's valid in most cases. Okay. All right, and so that's the perfectly insulated boundary condition. Okay, and so that's another one that's used fairly often, just because it's a nice approximation. All right, and so now let's go over convection. Okay, probably one of the more important boundary conditions that you can use in Ansys. Okay. All right, and so convection, if you remember from 407, is heat transfer to some kind of moving fluid. Okay. And so, this is often used in engineering if you have a part that's cooled by water or cooled by air, right? And so let's say that, you're doing a finite element simulation of the inside of your gaming rig or some kind of computer, okay? And so all the chips and all the electronic parts in there are cooled by a fan, right? And so that heat transfer from the computer to the cooling air, that's convection, okay? Right, and so schematically, usually we illustrate it like this. And so we have some kind of surface, okay? And the surface is at some kind of temperature, we'll call it TS, right? And then over the top of this, we have some kind of moving fluid that looks like this, okay? Right. And so this moving fluid, we have two properties that we need to quantify. We have the property H, and we have the property T infinity. And I'm going to define both of those on the next page. Okay, but because we have this moving fluid over the surface, what we usually have is some kind of heat transfer that comes out just like that. Okay. Okay. So any questions on this so far? Okay. And so the equation that we use to govern convection heat transfer is known as Newton's law of cooling. And it says that the heat transfer due to convection this is equal to H times A times the difference in temperature between the surface and the fluid temperature. All right. And so let's go ahead and define all of these terms here. Okay. So let's start from the right and go left, actually, because that makes things a little bit easier. Okay. All right. So first we have T infinity. Okay. And so T infinity here, this is going to be the temperature of our fluid. Right. And so whatever temperature the fluid is at, this is what you need to specify here. Okay. And it's worth noting that this is a parameter that you have to apply in Ansys. Okay. Okay. And so if you apply a convection boundary condition within Ansys, you have to specify what the fluid temperature is. Okay. And so that's one of the essential quantities. Okay. Next we have TS, right? And so TS is the surface temperature. Okay. And so the surface temperature, this is something that's going to be automatically computed from Ansys. Okay, so you don't have to worry about that. In fact, that's going to be one of your unknowns, right? Because the Ansys is going to compute the temperature all over your surface. Okay. Next, we have A. I'm not going to write A down there because A is just the area. Okay, surface area. And so that's straightforward. And so there's not much to say there. Okay. And the last quantity we have here is H. Okay. Mysterious H. Okay. And so H here is the convection coefficient. And so the convection coefficient is a parameter that you can set, and so this is also required by Ansys. And what the convection coefficient defines is how much or how strong is the convection heat transfer. Okay. And so this is required for Ansys. Okay, so this is something else that you have to specify. Okay. And so in total, when you're applying a convection boundary condition in Ansys, which more than likely you will be, unless you're doing like a satellite or something like that, is you need to specify the fluid temperature. Okay. And so that's one thing you have to specify. And you have to specify the convection coefficient as well. Right? And you'll see in the example later that we have to, specify both of these. Okay. So any questions on this so far? Okay. All right. And so how do we select these? And so the fluid temperature, more or less that's fairly easy to determine. Okay, because that's usually not too hard to imagine. Because a lot of times, if your part is being cooled by room temperature air, you can just set the air temperature to be room temperature. Okay, and so the thing that's actually really difficult is this convection coefficient. Okay, and so in order to find good values for the convection coefficient, you're going to need to use some techniques from your heat transfer class. Because in reality, the factors that go into this convection coefficient are very complex. Okay, because a lot of it depends a lot on the fluid mechanics of the convection. It depends on the fluid mechanics. It depends on the properties. It depends on the temperature. Okay, there's a lot of factors that go into this convection coefficient. Okay, and so the best way to estimate this is to you can use your knowledge from EGME 4.7 or any other heat transfer class that you've taken before. Okay. Or another way that you can do this is you can look up some published data. Okay. If you're lucky and you're doing if you're doing an FEA on on a situation that's pretty similar to someone else, and they've published their convection coefficient, you can go ahead and use that. Okay, and so that's usually perfectly fine. But more than likely, what you're going to have to do is you're going to have to determine the convection coefficient numerically or computationally. And so, in other words, you're going to have to run a different simulation in order to compute this this convection coefficient. Okay, and so this convection coefficient by far is I think the most difficult part of doing heat transfer simulations, especially the ones that involve convection. Okay, because a lot of times your results are going to be very sensitive to this parameter, and so you really have to nail it in order to get your heat transfer simulations to be accurate. But getting it really accurate can be really difficult without without the help of software. Okay, and so unfortunately, that's kind of where my knowledge of this ends, because I'm not as big an expert in heat transfer simulations, but I do know that it's possible to do it with simulations. I just haven't done it in Ansys before, and so it would have to be something that I have to look up. It would probably involve the fluid mechanics solver. Fluent in some way, because the convection coefficient depends on the flow, whether it's laminar or turbulent or things like that. Okay. And so convection coefficient, it's something that you have to specify in Ansys, and you might have to be a little bit clever in how you come up with this. Okay. But your results probably will depend strongly on this convection coefficient, so just kind of be aware. Okay, so any questions on this before we move on to radiation? Okay. All right, and so let's move on to the last mode of heat transfer that we have, which is radiation. All right. And so I'm not sure what your 407 classes are like, but for the one that I teach, radiation's it's a little bit of an afterthought. So it's we kind of go over it and we kind of squeeze in as much as we can at the end of the class, but we don't really have enough time to give it a lot of detail. And so because of that, my knowledge of radiation, my knowledge of heat transfer in general is not that strong, but radiation is even tinier than that. So you have to look at kind of a microscope to see. But for using radiation within Ansys, just a basic kind of understanding of it is usually good enough. Okay, and so radiation is kind of the black sheep of the heat transfer family, and so it transfers heat in a way that's kind of very different than conduction and convection. The way that radiation does it is through electromagnetic waves. Okay. And this is significant because electromagnetic waves don't need any kind of material medium in between. Okay. And so radiation can actually transfer heat in a vacuum. And in fact, radiation actually works best in a vacuum. Okay. I spelled vacuum wrong. Right. And so probably the most famous example of radiation is, just walk outside, right? And so, all the heat that the sun gives to the earth, that has to travel through space via radiation, because there's no matter, and there's no particles in between the earth and the sun, right? And so the only way for the heat from the sun to reach the earth is through radiation, okay? Right. But the sun isn't the only object that can give off radiation. And in fact, every object, no matter what temperature it is, as long as it's not at absolute zero, will give off radiation. Okay. Okay. And so the amount of heat transfer from radiation is given by the following formula. Okay. And so it is Q is equal to epsilon sigma times Ts to the fourth minus T infinity to the fourth. Okay. All right. And so let me go ahead and define all of these parameters here. Okay. Epsilon here is the emissivity. Emissivity here is a property of the surface. Okay. And so this defines how well that surface is at giving off radiation. Okay. And so it can be something in between 0 and 1. Okay. And so 1 is kind of the best value that emissivity can be. Okay. And so that tells you that the object is a perfect emitter. Okay. But emissivity of 1 is kind of a theoretical unachievable thing, right? Because the only objects that have an emissivity of 1 is known as a black body, which we've gotten close to approximating a black body, but I don't think there's a perfect one out there in existence. Okay. Whereas if you think of something like sandpaper, right? So sandpaper is like a very rough, coarse surface that probably won't emit that much radiation because its surface is pretty rough. All right, but you can look up the emissivity, and in material data sheets for certain kinds of materials. All right, and so sigma here, this is known as the Stefan Boltzmann constant. Okay. And so the Stefan Boltzmann constant is just a one of those constants that are out there. So it has a known value. I don't have it in front of me, but it's something very, very small. Okay. And the Ts and T infinity, what those are. That's the surface temperature and the ambient environment temperature. Okay. The only thing to note here is that if you're going to use this formula, your temperatures here have to be in absolute units, and so that that doesn't mean that that doesn't mean it's a chunker. What it means is that it's you have to use a temperature scale which has 0 at absolute 0, and so the most popular one here is Kelvin. Okay, and so because we're raising this temperature to the 4th power, if you use things like Celsius or degrees Fahrenheit, you're going to get an incorrect solution. Okay? And so the temperatures here have to be in Kelvin, right? But for Ansys, you don't have to worry about this because Ansys will handle that for you. But in case you were wondering, about that. Okay. All right, and so in general, the amount of radiation that an object gives off is generally pretty small. Because the Stefan Boltzmann constant is such a small number, and so really, the only times that radiation is really significant are when the surface temperatures are really, really high, and so you're talking like furnace level, fire level temperatures. Okay. Or you're in a situation where conduction or convection can't take place. Okay, and one of the most famous examples of this is in space, right? Because in space there's no matter, and so the only heat transfer that can come off like your satellite or rocket ship or something like that is through radiation. Okay, and so most times you can ignore radiation, and it's very reasonable just to leave it off your analysis. But if you're in one of those special cases, you want to make sure that you include it. Okay. All right, and applying radiation is in Ansys is very simple. I think the only thing that you have to apply here is the emissivity. Okay. But everything else Ansys kind of handles for you. Okay, so any questions on this? Okay. All right, and so there's one more property that I want to go over before we leave for today, and that's this idea of internal heat generation. Okay. And so thermal generation is a way so that you can generate heat within your Ansys part. Okay. And so if you have some kind of chemical reaction happening within your Ansys part, or maybe electrically it's being heated one way or the other, you can apply internal heat generation through Ansys. Okay. Okay. And so one example of this is let me go back to our combustion chamber. And if you want to do a heat transfer simulation on the air inside that combustion chamber, you can model your combustion reaction as kind of some internal heat generation. As the combustion reaction takes place, it releases that thermal energy, and then you can account for that in your simulation. Okay. All right, and so but in a lot of cases, internal heat generation is not that common, and so I'm not going to go too much in depth, just for the sake of brevity. But just know that feature is out there for you to use. Okay. Okay. So any final questions on this before we wrap up for today? All right. Questions?
So if we want to get some ask you for some help on the final project, when would be a good time to do that?
Anytime. Just send me an email, send me a message on Discord, and then we can either meet in office hours, or we can set up a meeting outside of that to discuss your project. Yeah.
Okay.
Yeah.
Okay.
Yeah, and please let me, and please and please make sure you guys are working on your projects, because the sooner you kind of work on things, everyone kind of runs into issues, one way or the other, either with the meshing or with the boundary conditions. And so, the sooner that you start, the sooner that you can reach out to me, and I think the sooner that we can kind of work through those issues. Because generally what happens is that I get most of the issues happening right before the deadline. And so the sooner that you start, I'm usually a lot more free over these next couple of weeks to help people out with issues. But right before the deadline, it becomes a bit hard to kind of reach everyone. And so, definitely start sooner than later. Oh yeah, Ronald's in 3 of my classes, and so he has a lot of projects. Okay, so that's all we got time for today. So thank you guys for tuning in. Thursday, we're going to do our Ansys activity on topology optimization. And again, it's going to be an optional activity. And so I'm going to send an email out to confirm that. Yeah, and so, from here on out, it's just all Ansys stuff. So hope you guys enjoy the rest of your evening, and I'll see you guys on Thursday.
Good night, or good day, or whatever.
Thanks, you too.
Professor?
Yep.